You think your coffee is hot, don't you? Of course it is. You can feel it. The steam rising, the warmth against your lips, the way it burns your tongue if you're not careful. Hot. Obviously hot. And that ice cube in your freezer? Cold. Definitely cold. Touch it and your finger goes numb. But what if I told you that neither your coffee nor that ice cube has any temperature at all? Basic stuff. Hot and cold are the most fundamental sensations you have. But here's a question that's going to completely unravel your understanding of temperature. What makes something hot? Where does the hotness live? Is it in the coffee itself? Is it a property the coffee has, like its color or weight? And here's the really disturbing question. If you could zoom in and look at a single molecule of that coffee, would that one molecule be hot? Most people have never really thought about this. They just accept that hot things are hot and cold things are cold. But when you actually ask what temperature is, when you dig into what's really happening when something feels hot or cold, you discover something so strange that it changes everything you think you know about the world around you. Temperature doesn't exist, not the way you think it does. What you call hot and cold are not properties that objects have. They're statistical averages of something completely different. And once you understand what's really going on, you'll realize that the entire concept of temperature is a useful fiction we've created to make sense of a reality that's far weirder than it appears. Let me show you what I mean. Here's a simple experiment. Fill one bowl with hot water, one with ice water, and one with lukewarm water. Put your left hand in the hot water and your right hand in the ice water for about a minute. Now quickly put both hands in the lukewarm water. What do you feel? Your left hand feels cold, your right hand feels warm. Same water. Two completely different temperature experiences. How is that possible? If temperature is a real property of the water hasn't changed, the molecules are moving at exactly the same speed they were a second ago, but your experience of its temperature is completely different depending on what your hands were doing before. This should be your first clue that temperature isn't what you think it is. If you're curious about how the most basic concepts we take for granted turn out to be completely different from what they seem, and you should be, because understanding this reveals the hidden nature of everything around you, consider subscribing to Reimagine the Physics. We explore how the familiar world dissolves when you look closely enough, revealing the strange reality underneath. Hit that notification bell and share this with someone who thinks they understand what hot and cold mean. They don't. None of us do, until we see what's actually there. Now let's zoom in and see what's really happening when you touch that hot coffee. You think you're feeling the coffee's temperature, but you're not. You're feeling the speed of molecules. Coffee is made of molecules, water molecules, sugar molecules, caffeine molecules, all jiggling around constantly. And when I say jiggling, I mean really jiggling, fast. The molecules in your hot coffee are moving at about 500 meters per second. That's faster than the speed of sound. But here's the key point. They're not all moving at the same speed. Some are moving faster, some slower. Some are moving at 300 meters per second, some at 700 meters per second. The speeds are all different, constantly changing as molecules crash into each other, speed up, slow down, change direction. What you call temperature is just the average speed of all these molecular motions. That's it. Temperature is a statistical average of kinetic energy. It's not a property that individual molecules have. It's a property that emerges when you have trillions and trillions of molecules all moving at different speeds. Think about what this means. A single molecule cannot be hot or cold. It can be moving fast or slow, but it cannot have a temperature. Temperature only makes sense when you're talking about enormous numbers of molecules, so many that you can calculate a meaningful average. Your coffee contains about 10 to 25 molecules. That's 10 followed by 25 zeros. More molecules than there are stars in the observable universe. When we say the coffee is hot, we mean the average kinetic energy of those 1025 molecules is high. But individual molecules, they're just moving, some fast, some slow, constantly changing. None of them is hot or cold. The hotness only exists in the average, in the statistical summary of all their motions. This is why that experiment with the 3 bowls works. When your left hand was in hot water, the fast-moving water molecules were transferring energy to the slower-moving molecules in your skin. When your right hand was in cold water, energy was flowing the other direction. Your nervous system interprets these energy transfers as temperature. But when you put both hands in lukewarm water, the comparison changes. Your left hand, which had been receiving energy from faster molecules, now encounters slower molecules. The energy transfer reverses, and your nervous system interprets this as cold. Your right hand experiences the opposite. Same water, same molecular speeds, same actual average kinetic energy, but completely different temperature experiences because temperature perception is about energy transfer rates, not about some intrinsic property of the water. Now, here's where it gets really strange. If temperature is just an average, what happens when you have very few molecules? Imagine you could isolate just 10 water molecules. Could you meaningfully say those 10 molecules have a temperature? Not really. With only 10 molecules, 5 might be moving fast and 5 might be moving slow. The average isn't very meaningful, it fluctuates wildly as the molecules interact. What about 100 molecules? Still not very stable. The average keeps changing significantly. What about 1,000? Better, but still fluctuating quite a bit. Temperature only becomes a reliable, stable concept when you have enormous numbers of molecules, millions, billions, trillions. Only then does the average kinetic energy become stable enough to call it a temperature. This reveals something profound. Temperature is an emergent property. It doesn't exist at the level of individual atoms or molecules. It only emerges when you have massive numbers of particles, so many that statistical averages become meaningful. But let's push this further. If temperature is just an average of molecular motion, and if individual molecules don't have temperature, then what happens at absolute zero? Absolute zero is the temperature at which molecular motion stops completely. Zero kinetic energy, zero motion. At absolute zero, molecules would be perfectly still. But here's the problem. Quantum mechanics won't let you do this. The uncertainty principle says you can't have a particle with both perfectly defined position and perfectly defined momentum. If molecules were perfectly still at absolute zero, they would have perfectly defined momentum, zero, and would need to be in perfectly defined positions. The uncertainty principle forbids this. So even at absolute zero, molecules must retain some motion, what's called zero-point energy. They can never be completely still. This means you can never actually reach absolute zero. You can get close, very close, but never quite there. Temperature has a lower limit but no upper limit. There's a coldest possible temperature, which you can approach but never reach, but there's no hottest possible temperature. In principle, you could make molecules move arbitrarily fast, giving you arbitrarily high temperatures. The hottest temperature ever created by humans is about 5 trillion degrees Celsius, achieved for microseconds in particle accelerators when heavy atomic nuclei collide. At those temperatures, normal matter breaks down completely. Atoms disintegrate into their constituent particles. But even at these extreme temperatures, the concept remains the same. Temperature is still just the average kinetic energy of particles. It's just that at these energies, the particles are quarks and gluons instead of atoms and molecules. Now let's think about what this means for heat transfer. When you hold a hot cup of coffee, why does your hand warm up? The fast-moving molecules in the coffee collide with the slower-moving molecules in your skin. In these collisions, kinetic energy is transferred from the fast molecules to the slow ones. The coffee molecules slow down slightly, the coffee cools a tiny bit, and your skin molecules speed up, your hand warms up. Heat transfer is just kinetic energy transfer between molecules. When molecular speeds average out between two systems, we say they've reached thermal equilibrium, the same temperature. But here's what's crucial to understand. No heat is flowing. No temperature is moving from one place to another. What's happening is that kinetic energy is being redistributed through molecular collisions until the average kinetic energy, temperature, is the same everywhere. The coffee doesn't lose its hotness to your hand. The fast-moving coffee molecules lose some kinetic energy to slow-moving skin molecules. The coffee gets a little cooler, your hand gets a little warmer, until the average molecular speeds match. Think about a hot stove burner. You think it's radiating heat, but what's actually happening? The fast-moving atoms in the metal are causing electromagnetic radiation, infrared photons, to be emitted. These photons carry energy. When they hit your skin, they cause your skin molecules to move faster. You interpret this as warmth. No heat moved from the stove to your skin. Energy moved in the form of electromagnetic radiation. That energy caused molecular motion in your skin. Your nervous system interpreted the increased molecular motion as temperature. Even more strange, That infrared radiation traveling from the stove to your skin has no temperature at all. Photons don't have temperature. They can't. Temperature is average kinetic energy of matter, and photons aren't matter. They're massless packets of electromagnetic energy. The photons carry energy, but they don't carry temperature. Temperature gets reconstructed on your end when the photon energy gets converted back into molecular motion in your skin. This is why space has no temperature. Space is mostly empty, no molecules, no matter. Without matter, there's nothing to have kinetic energy, so there's no temperature. You can't have hot space or cold space, only hot or cold matter in space. But wait, you might have heard that space is cold. Spacesuits need heating. Spacecraft worry about freezing. How can space be cold if it has no temperature? Here's the key. Space isn't cold. Space provides no insulation. If you put a warm object in space, it will radiate its energy away as electromagnetic radiation. With no molecules around to give energy back, the object cools down by radiation until it reaches the temperature of the cosmic microwave background, about 2.7 degrees above absolute zero. The object gets cold in space, but space itself isn't cold. Space is just empty. The object loses energy through radiation, and with no surrounding matter to replace that energy, it keeps cooling down. Now let's bring this back to your everyday experience. When you say your coffee is hot, what you really mean is that the average kinetic energy of the molecules in your coffee is higher than the average kinetic energy of molecules in your tongue. When you say the ice cube is cold, you mean the average kinetic energy of the water molecules in the ice is lower than the average kinetic energy of molecules in your finger. Hot and cold aren't properties of objects. They're relationships between the average molecular kinetic energies of different systems. Temperature is always relative, always comparative, always about energy differences between molecular populations. But here's the deepest realization. If temperature is just a statistical average of molecular motions, then temperature doesn't exist at the fundamental level of reality. It's what physicists call an emergent property, something that only makes sense when you zoom out and look at huge collections of particles. Individual molecules don't know about temperature. They just move, collide, speed up, slow down, change direction. Temperature is something we calculate by taking the average of all these individual motions. It's a useful concept for describing the behavior of matter and bulk, but it's not a fundamental feature of reality. This is true for many of the concepts we use to describe the world. Pressure, for example, is just the average force of molecular collisions against a surface. No individual molecule exerts pressure. Pressure emerges from trillions of molecular impacts per second. Viscosity, how thick or thin a liquid is, emerges from how easily molecules slide past each other. No single molecule is viscous. Viscosity is a bulk property that emerges from molecular interactions. Even concepts like solid, liquid, and gas are emergent properties. They describe how large numbers of molecules behave collectively, but individual molecules aren't solid or liquid or gas. They're just molecules, interacting according to the electromagnetic force. Let's make this concrete with some examples that will completely change how you think about the thermal world around you. Consider an ice cube. You think it's cold because it's ice. But what's really happening? The water molecules in the ice are moving more slowly than the molecules in your finger. They're also locked into a rigid crystal structure by hydrogen bonds. But each individual water molecule is just vibrating in place. None of them is cold. The coldness emerges from the statistical average of all their vibrational motions. Now watch what happens when the ice melts. As you add energy, by warming it, the molecules vibrate faster and faster. Eventually, they're vibrating so vigorously that they break free from their rigid crystal positions and start moving around each other. The ice becomes liquid water, but here's the key insight. There's no sharp boundary between solid and liquid at the molecular level. Some molecules are still vibrating in roughly fixed positions while others have broken free and are moving around. The phase transition from solid to liquid is a statistical phenomenon. It happens when enough molecules have gained enough kinetic energy to break free from the crystal structure. At the exact melting point, you have a mixture, some molecules behaving like they're in a solid, others behaving like they're in a liquid. The ice cube doesn't suddenly switch from cold to not cold. The average kinetic energy gradually increases until statistical mechanics says this is now mostly liquid behavior. The same thing happens when water boils. Individual molecules don't suddenly become steam molecules. They gain enough kinetic energy to escape the liquid entirely and move freely through space. Boiling is just the point where the average kinetic energy is high enough that a significant number of molecules can break free from the liquid surface. Phase transitions, melting, boiling, freezing, aren't fundamental changes in the nature of molecules. They're statistical transitions that happen when average kinetic energies cross certain thresholds. Now let's talk about something that might completely blow your mind: the kinetic theory of gases. You know how gas exerts pressure on the walls of a container? You might think it's because gas wants to expand or has some inherent pressure property. Wrong. Gas pressure is just molecular bombardment. The gas molecules are flying around at high speeds, hundreds of meters per second, constantly colliding with the container walls. Each collision delivers a tiny force. Trillions of collisions per second create what we experience as steady pressure. No individual molecule exerts pressure. Pressure emerges from the statistical average of countless molecular impacts. And the faster the molecules are moving, higher temperature, the harder they hit the walls, higher pressure. That's why heating a gas increases its pressure. But here's what's truly remarkable. You can calculate gas pressure exactly using nothing but Newton's laws of motion and statistics. You don't need any new physics, any special gas laws, any mysterious pressure forces, just molecular motion plus statistical averaging. Take a box of gas, count the molecules, calculate their average speed from the temperature, figure out how often they hit each wall, calculate the average force per collision, multiply by the collision rate, you get the pressure. Exactly. No approximation, no special assumptions, just statistics and molecular motion. This was one of the greatest triumphs of 19th century physics, showing that the thermal properties of matter, temperature, pressure, heat capacity, phase transitions, could all be explained as statistical consequences of molecular motion. No thermal fluids, no mysterious heat substances, no special thermal forces, just molecules obeying Newton's laws, with thermal properties emerging from statistical averages. But let's push this even further. What about heat capacity? How much energy it takes to warm something up? Different materials have different heat capacities. Water takes a lot of energy to heat up. Metals heat up more easily. Why? It all comes down to how molecular kinetic energy can be distributed. In a simple gas like helium, molecules are just points flying around. All the kinetic energy goes into translation, moving from place to place. But in more complex molecules, there are more ways to store energy. A molecule like water can not only move from place to place, it can also rotate and vibrate. This is why water has such a high heat capacity. Water molecules can translate, rotate, and vibrate in multiple ways. When you add energy to water, it gets distributed among all these different types of molecular motion. More ways to store energy means higher heat capacity. But individual atoms and electrons don't have heat capacity. Heat capacity is a statistical property that emerges when you have enormous numbers of particles with different ways to store kinetic energy. Now let's consider what happens at very high temperatures. As you add more and more energy to matter, molecules move faster and faster. Eventually, they're moving so fast that molecular bonds start breaking. The matter breaks down into individual atoms. Keep adding energy, and eventually the atoms themselves break apart. Electrons get stripped away from nuclei. You get what's called a plasma, a mixture of free electrons and atomic nuclei, all moving at extremely high speeds. But throughout this entire process, from molecules to atoms to nuclei, the concept of temperature remains the same: average kinetic energy of whatever particles you have. The particles change, but temperature is always statistical motion. Here's another way to see how strange temperature really is. Consider a perfect vacuum, completely empty space with no matter at all. What's the temperature of empty space? The question doesn't make sense. Temperature requires matter, particles with kinetic energy that can be averaged. No particles, no kinetic energy, no temperature. Empty space doesn't have a temperature. But suppose you put a single atom in that empty space. Does that one atom have a temperature? Not really. Temperature is an average, and you can't calculate a meaningful average from a single data point. Temperature only becomes meaningful when you have vast numbers of particles, enough that statistical averages become stable and predictive. This is why temperature is fundamentally different from properties like mass or charge, which individual particles can have. Temperature is irreducibly statistical. The world you experience, hot coffee, cold ice, warm air, cool water, is a world of emergent properties. These properties seem real and fundamental because they're so consistent when you have enormous numbers of molecules, but they disappear when you zoom into the molecular level. At the smallest scales, there's no temperature, no pressure, no viscosity, no phases of matter. There are just particles moving and interacting according to the fundamental forces of physics. Everything else, all the thermal properties you experience every day, is statistics. Your hot coffee is a statistical summary of 10 by 25 molecules moving at an average speed of 500 meters per second. The hotness isn't in the molecules, it's in the numbers, in the averaging, in the emergence of statistical regularity from molecular chaos. This doesn't make temperature less useful or less real as a practical concept. Temperature is incredibly useful for describing and predicting how matter behaves. We can measure it precisely, control it carefully, use it to design everything from engines to refrigerators to computer chips. But understanding that temperature is statistical rather than fundamental changes how you see the thermal world around you. That hot stove isn't intrinsically hot, it's a collection of fast-moving atoms. That cold drink isn't intrinsically cold, it's a collection of slow-moving molecules. You're not feeling the properties of objects when you feel hot and cold. You're feeling the statistical summaries of vast numbers of invisible molecular motions. Temperature is your nervous system's way of experiencing the statistical mechanics of matter. Every time you reach for a hot cup of coffee, you're interacting with one of the most profound concepts in physics, the emergence of macroscopic properties from microscopic statistics. The hotness you feel is the macroscopic manifestation of molecular kinetic energy averaged over numbers too large to comprehend. Subscribe to Reimagine the Physics if you want to keep exploring how the familiar concepts that structure your everyday experience dissolve when you examine them closely enough. The deeper you dig into the nature of heat, cold, and temperature, the stranger the relationship between the microscopic and macroscopic worlds becomes. You can't unfeel this now. Every time something feels hot or cold, you'll know you're not feeling a property of the object. You're feeling your nervous system's interpretation of statistical molecular motion. Temperature isn't in the things around you, it's in the numbers, in the averages, in the statistical emergence of thermal properties from molecular chaos. The hot and cold world you experience is real, but it's not fundamental. It's emergent, statistical, and far stranger than the simple thermal sensations that seem so obvious and immediate. Reality isn't what you feel. What you feel is what your nervous system constructs from statistical mechanical information about molecular motion. And that construction reveals something beautiful. The macroscopic world of human experience emerging from the microscopic world of atomic motion through the power of statistical averaging.